So my computer decided that it was going to update this morning, and then it was like the slowest update ever, so I turned it off and on, and now it's undoing what it was doing. Oh, I think maybe it's going to do something now. So until it decides it's going to cooperate with us, I'm just going to use the board, the old-fashioned board, instead of the PowerPoint. I know. Woo.
Can you just draw the picture?
Going back in time. Yeah, no. There's a reason why I teach science and not art. Here you go. And we will start with devotions. Oh, good. It's starting back up now. So I am reading through the Bible this year. I'm almost into the New Testament. By the end of the month, we've made it all the way through the Old Testament. Has anyone read through the Bible completely? This is actually my first time reading through the Bible in its entirety. And I have to admit, there are parts that I'd never read before. Specifically, yeah, okay, that I knew. Specifically, some of them like minor prophets, and actually what I found is that my Bible had a printing error in it, where the last like minor prophets, Zechariah, Haggai, and Malachi, are like when they did the binding, they like clipped it wrong, and so they're all like messed up. So it's like Haggai 2, Malachi 1, like however they did the binding. And I was like, well, I didn't know that before because I'd never read those before. So it's been very interesting. One of the things that stood out to me over this past few weeks was in Daniel, and I have read Daniel several times, but Daniel chapter 3, specifically this is the story of Shadrach, Meshach, and Abednego, or focuses in on them, where they're asked to, or well, they're not asked, they're told by mandate, King Nebuchadnezzar, to bow down and worship this idol that he had made in the image of himself when the music plays and everything, and they don't. And so then someone rats them out. So King Nebuchadnezzar sees it upon himself to address the issue. Like, he's pretty upset about this, that they would be so defiant and not bow to his idol. And so this is Nebuchadnezzar he's like giving them an opportunity to do what he sees as the right thing, to just bow down to the idol and obey him. So he's giving them this opportunity. And he wraps it up by saying, if you do not worship, you will be thrown at once into the midst of a furnace of blazing fire. And what God is there who can rescue you out of my hands? Woo! Talk about arrogance. He is the king of pride, Nebuchadnezzar is, for sure. Shadrach, Meshach, and Abednego answer the king, and I love their response. They say, "Oh, Nebuchadnezzar," they're a little sassy here, "we do not need to answer you on this point." So they say, it's like, whoo, they're like giving it back to him. They're not scared at all. "We do not need to answer you on this point. If it be so, our God, whom we serve, is able to rescue us from the furnace of blazing fire, and he will rescue us from your hand, O king. But even if he does not, let it be known to you, O king, that we are not going to serve your gods or worship the golden image that you have set up." And I love their response because they do not cower. They do not cower in fear. They know there's a spot right up here, or there's a spot over there, kind of hidden in the corner. They know where their confidence comes from, and it comes from God. And they are not going to cower in fear. And so they tell Nebuchadnezzar this. And what I love about their response is that they make sure it's known to Nebuchadnezzar that God is able. But they don't actually tell him outright that he will. They say he is able. He can do this, but they don't know if it's the will of God to save them or not. They don't know. Like, maybe it was their time to die. Maybe they were going to die a martyr's death. I mean, that does happen. It's not like everyone who believes in the Lord and has confidence in him is always going to escape death. Like, that does happen. And so escape earthly death. We escape eternal death. But they say, if he is able, and then they follow it up with, but even if he doesn't save us, we're still not going to bow knee to your God. So I love that response. I feel like it's a really, really good response, because when we pray, we are told to pray in accordance with God's will. We're not, God isn't a genie that's just there to grant our requests. And sometimes it's yes, and sometimes it's no, and a lot of times it's wait. And so we have to approach God with that mentality of, you are able to do this, but even if you don't, I still trust you're sovereign. I still trust you know what you're doing. I still put my trust in you, which I think is a very important distinction to make. Let's pray. Dear Heavenly Father, we thank you for this day that you've blessed us with. We're able to gather together to continue our study of chemistry. Lord, we thank you that you are sovereign, that you are all-powerful, that you hold everything in your hand, Lord. Help us to approach you as such. Help us to approach you in a way where we fully understand that you are able to do anything and everything, but sometimes you choose not to. For whatever reason, it is in accordance with your will, Lord. Help us to have that understanding and to not let that deter us from putting our full trust in you, because you are worthy of it. Bless our time together. Just help me to teach today with clarity, and help help the students to understand. In Jesus' name, amen. Okay. It looks like I love technology, but sometimes I tell you, it's like doesn't matter. I'm going to grab you your notes here. I actually should make sure it's picking me up. Okay, so it looks like people were turning their homework in. I didn't check this morning to see that everyone had turned in their assignments, but you do have until the end of the day if you didn't get something in. Are there any questions about the Google Classroom? Yes?
What am I supposed to hand in for the intro to chemistry lab? Because we did that all last week.
Yes.
I completed it.
Yes.
I have the paper. Do you want me to do paper?
Ideally, if you could take a picture and just attach it to the Google assignment,
Yeah.
so that I'm not collecting just a loose paper. Yes, though that was the idea. That's where you're supposed to turn that in. So if you brought it with you today, if when you get home you could take a picture or scan that in so that it's there for me to grade on there. Are there any other questions? Now we'll see if it'll find my computer. The remote to this TV also was missing this morning. I really want this to work because I found such cool graphics this week too. Nope. Nope. Okay, we're going to try one more, and then we're just going to go to the board. I think that was it. Yes! Okay, so last week we introduced kind of some of the history of chemistry. We looked at what chemistry is. This week we're going to be looking at chapter 2 and some of the fundamental aspects of, gosh, this is working like a snail. I apologize, guys. Does not want to open. Some of the properties of matter. So Lily decides to open my PowerPoint. Let's redefine what, or not redefine, but define again what matter is. So matter is anything that takes up what? Space. Anything that takes up space. So that's your first blank there. And it also has to have what? Mass. There we go. Okay. And we're up. There we go. Only took 10 minutes. So matter is anything that takes up space and has mass. So matter has a couple different categories, or well, scientists you're going to find love to put things in categories. So matter is parceled off into two main categories, pure substances and mixtures. And I included a little graphic there in your notes to kind of show you how we categorize different matter as a pure substance or as a mixture. So pure substances are going to consist of only one type of matter. And this type of matter cannot be separated by any other kind into any other kind of matter by specifically something known as a physical means. And we're going to get into what that means in more detail here in a few minutes. Things that fall under the category of pure substances are elements and compounds. So elements are the purest substances. They're things like oxygen and carbon and gold and iron. And compounds are combinations of elements like carbon dioxide or sodium chloride. Now, even though carbon dioxide is technically a combination of two elements, carbon and oxygen, it's still considered a pure substance because it is its own unique thing. And it behaves differently than carbon or oxygen do on their own. And if I was to break carbon dioxide down into carbon and oxygen, it would no longer be carbon dioxide. So carbon dioxide, even though it's a combination, is still considered a pure substance because it is unique unto itself. Now, a mixture is a material that can be separated by physical means into two or more pure substances. So in a mixture, things aren't what we would say chemically combined. So I can have a mixture of salt and sugar, which would be very deceiving because it would all look the same, especially if it's white sugar. But I can have a mixture, but technically in that mixture I have salt and I have sugar, right? They're two different things. They're not chemically combined, they're just hanging out together in the same beaker or bowl or whatever. Or let's use something a little bit bigger. I can have a mixture, this also would be cruel, of M&Ms, Skittles, and Reese's Pieces. That would be a cruel thing to do to someone. But you can have a mixture where they all kind of look the same, but each is its own unique, distinct candy, and you could separate them out. It'd be tedious, but you could do so. So we've used the term physical in these definitions. And here's the chart that is also in your notes that kind of shows how matter has two branches, pure substances and mixtures. And then underneath pure substances, we have elements and compounds. And underneath mixtures, there are two different types of mixtures, depending on whether you can see the individual parts or you can't. So we'll get to defining the differences between those in just a minute. So we use the term physical by physical means in the definitions of both a pure substance and a mixture. What does that mean? A physical means? Well, all matter has properties. Okay? It has physical properties and it has chemical properties. And there's distinction of the two, obviously, otherwise there wouldn't be two different categories. So the properties of matter, its distinguishing characteristics. Physical properties tell how a substance is by itself. They can be measured without changing the substance into another substance. So you can measure a physical property without changing the identity of the substance you're measuring that property of. So I can look at salt and I can look at sugar, and they're going to be very similar in appearance. They're both going to be white, crystalline solids. Okay, all of those things, white, crystalline, solid, those are all part of its physical properties. Some other things that can be physical properties that are a little less known, a little less well known. Okay, density, that one's probably pretty well known, but that's looking at how many particles are packed into a material. So it's the amount of matter packed into a given volume. So it's what makes, a cube of foam different than a cube of the same size of iron. One's going to be really light, the other is going to be really heavy. And that has everything to do with the density, how tightly packed the individual atoms or molecules of the substance is to each other. So in a given space, how tightly packed the matter is. One is more dense than the other. And that is a property that can be measured without changing the identity. I can pick up the iron, I can pick up the foam, and I can just immediately tell one is denser than the other. Malleable is something that's easily hammered into shapes. Okay, just because I change the shape of something, I don't change the identity of it. Okay, I can take gold and I can hammer it into all kinds of shapes, into rings and earrings, and I can use it to, gild things, when they just cover things with kind of like a very thin sheet of gold. It's all gold. It takes different shapes, but it's still gold. Just because it's a different shape doesn't change its identity. Ductility is the ability of something to be stretched into a wire. If I stretch something into a wire, I also don't change its identity, right? It's still that substance, it's just stretched into a wire. And then conductivity measures its ability to transfer heat or electricity between its particles. Okay, if something allows electricity to travel through it, like copper, it doesn't change the identity of copper to have electricity travel through it. It's just a property of copper that it can have electricity travel through it. So these are all properties that I can measure without changing its identity. And here are some other physical properties. So if you wanted to scribble these down in the margin, you don't have to, but these are kind of some other physical properties. Boiling point, what temperature something boils at. Color, texture, the temperature that it is. Okay, when I take the temperature of something, that's a physical property. It can be cold if it's outside in the snow. It can be warm if it's inside a room by a fire. It doesn't change it just because of its temperature's changed. The luster is the shininess of something. The hardness, well, that describes itself. Somebody wants to close that door. Extensive properties, these are also physical properties. They just kind of fall into a different category. Things like volume, mass, size, weight, length, all things that I can measure about a material, but doesn't change its identity just because I can measure it. So this is very, very important. This is like fundamental chemistry here. Having an understanding of physical versus chemical properties, which are the next type that we're going to, because physical does not change the identity. You can observe it. It doesn't change the identity. It feels like I've repeated that a bunch of times because I have, because it's important. Chemical property. Chemical property, if physical doesn't change the identity, then chemical property most likely is, right? It's going to change the identity. So a chemical property shows how a substance acts or reacts in the presence of another material. For a chemical property to become apparent, the material has to undergo some sort of change. So chemical properties basically are describing how something changes from one thing to another. Some examples, common examples. So there's lots of examples listed here, but kind of the three that are a little more practical application for us are going to be toxicity, if something's toxic or not. Reactivity, how reactive is it? Table salt is not very reactive. Okay, sulfuric acid, highly reactive. Bleach, very reactive. But the salt that you put on your food, very, very stable. Doesn't react with a whole lot of anything. Flammability, how easily something combusts or goes into a flame. So in that case, fire is the thing that's changing. It's the material, because it's not like if I take a piece of wood, it's not like I'm reacting the wood with something else to make it burn up, right? There's not another chemical that I've introduced. I've just set it on fire. But in the process of setting it on fire, I've taken that wood and I'm changing its identity. It's no longer wood, but it's carbon dioxide, water vapor, all the stuff that was making that wood, the compound that it was, and the things that were trapped inside of it, like the water vapor, are now breaking down and changing. And fire is the agent. It's the material that is changing the wood. And we'll talk a little bit in the future about what fire is, because that's kind of a neat thing. We won't bunny trail down that today, though. So fire, though, and heat can be a difficult thing sometimes, because obviously you can apply heat to something without changing its identity, right? You can apply heat and change its temperature, but not change its identity. So whenever fire is involved, because you're going to be given some examples in your textbook this week, and in your questions they'll be asking you, is this a chemical property? Is this a physical property type deal? Whenever fire is involved, you have to ask the question, did the substance's identity change? Or did it just heat up or cool down? Did its identity change? So there's the properties, which are the inherent, just kind of way the matter is. And then there are the changes. So a chemical property goes hand in hand with a chemical change. But physical property doesn't necessarily always go hand in hand with the physical change. So a physical change to something is going to change the state or the shape of that material. So when I say the state, what I'm talking about is the states of matter, like solid, liquid, gas. So everyone is familiar with the common states of matter, solid, liquid, gas, from a previous science class. So if I change the state of it, I take a solid and I turn it into a liquid, or I take a liquid and I turn it into a gas, or I take a gas and I turn it into a liquid, etc. Just because I've changed the state of something doesn't mean I've changed its identity, right? So solid carbon dioxide can become gaseous carbon dioxide in dry ice. That's what dry ice is. It's solid carbon dioxide that then becomes gaseous carbon dioxide. They're both carbon dioxide. One isn't more or less carbon dioxide. It's just changing its state. We're going to use water often as an example because it's something that we're very, very familiar with. And it's the only substance on planet Earth in the natural world that exists readily as all three states. Other materials are going to exist as one state, and in extreme circumstances might change states, but it's usually in the lab that we're changing the states of other materials, like carbon dioxide, okay? That's a gas, but under certain circumstances we can force it to become a solid if we get it really, really cold, but you're not going to find solid carbon dioxide just out in nature because it doesn't get cold enough to do that. But water, we readily experience in all three states. In fact, you can experience in all three states on a cold winter day, standing outside, drinking a hot cup of tea in the snow. I don't know why, maybe you just like to drink a warm beverage outside, I don't know, but you got a hot cup of tea, you're standing in the snow, you got solid water, you got liquid water, and you got the steam rolling off, which is vapor, water vapor, or gaseous water. All three are water. One is not more water than the other. They just are in different states. So a physical change is going to cause a change in state. It also can cause a shape change. So take, for instance, crushing a can. Just because the can is crushed, it's still a can. I haven't done anything to change the identity. It's just a useless can now. So it takes up a little space, I guess. Breaking glass doesn't change the identity. It's just broken, so it's lost functionality. Chopping wood, still wood, it's just in smaller pieces, making it easier to use. Shredding paper, still paper, it's just now in a bunch of different pieces. So changing state or shape. Now, a chemical change. A chemical change, also known as a chemical reaction. Okay, we're going to be using these a lot this year. This is going to cause a change in the identity of the material. So it's a change that results in a different material with a different composition and different properties. So there's going to be a change in identity. So some examples here. Iron rusting. Okay. An example of a physical change to iron would be taking it out of the earth and forging it into the pan. Okay, it's iron from the earth, turns into the iron pan. That's a physical change. But now I haven't taken very good care of it, and oxygen is reacting with the iron, and it started to rust. Burning wood. Chopping that wood was a physical change. Didn't change the identity of it. But now that I'm burning it, I'm changing the identity of the wood. So it's a chemical change. Metabolism, so breaking food down, it goes into your body as one thing and is broken down into its components and burned and used, and then anything that's not used comes out as something different, not what it went in as. Cooking an egg, okay, you're going to change the properties of those proteins that are in the egg, so anytime you cook something, it is a chemical change. You're doing chemistry in the kitchen whenever you cook. So baking a cake, electroplating things. A rotting banana is an example of just a natural chemical change that's occurring as compounds in the banana are breaking down as the banana ripens. So all good examples of chemical changes. The identity of something is being changed. So those are the physical and chemical properties and changes. Those are properties and changes that all matter experiences. So when we go back to looking at our pure substances, our elements and our compounds, they can undergo chemical changes, but you can't physically separate them. You can't physically do anything to gold to make it not gold anymore. You can chemically react it with something, but you can't physically do anything to it. You can't physically do anything to carbon dioxide to not make it carbon dioxide anymore. You can chemically do something to it, but not physically. When it comes to mixtures, however, the homogeneous mixture and the heterogeneous mixture, you can physically separate them through lots of different types of laboratory techniques, the most basic of which being you pick things apart with your hands because you could see, like in the Skittles and M&M's scenario. You can see the difference. It's tedious, but you can separate them. So there's two categories of mixtures, heterogeneous mixtures and homogeneous mixtures. The prefixes hetero and homo are common in science. Hetero always is going to be referring to different, so you can see that there's two or more different things in it, where homo is always going to kind of be in reference to the same, something that has the appearance of the same. Even if there's something different, it appears the same. So in a heterogeneous mixture, there are two or more distinct regions, which are called phases. In a homogeneous mixture, there are two or more, but it appears to only have one. So it appears the same throughout. So it appears, that's the key word here, to only have one phase. So notice how in heterogeneous mixtures, the particles are going to be, they're not going to be uniform, they're going to kind of be all over the place. This is what gives it its appearance of having different parts. Versus in a homogeneous mixture, the particles are going to orient themselves in an even distributed way. So they're going to be distributed uniformly, which is going to give them the appearance of being the same throughout. So some examples of a heterogeneous mixture, cereal and milk, okay, that's an easy one, ice and soda, soil. Okay, soil is a combination of little rocks and organic debris and sand and clay, and so there's lots of different types of particles in soil. Sometimes you can see them, sometimes it's harder to see them, but typically when you look at soil, you can see the individual little parts and pieces that make it up. So it's a good example of a heterogeneous mixture. If you've ever seen a granite countertop, maybe you have them in your home or you know someone who does, granite is also a really good example of a heterogeneous mixture. You can see the different, it's one rock, right? We call it granite, but technically it's a mixture of a lot of different type of rocks, and you can see the different type of rocks inside of it. And blood. Now blood is a little bit trickier because it can appear the same, but all you have to do is spin it really fast in something called a centrifuge, and the parts separate out very distinctly. And if you leave it in a bag even at room temperature, I believe it also would separate out eventually, which is why they keep it chilled. One of the reasons they keep it, well, and preservation. Homogeneous mixtures appear to only have one phase, so good examples of them are going to be salt water or sugar water. Okay, you don't actually know that there's salt or sugar in it until you go to take a sip. The ocean looks the same as Lake Michigan. Like, if you took a glass of water out of each one. Now, I mean, beauty-wise, there's differences in scenery and stuff, but if you took a glass of water out of each one, you wouldn't know that it's ocean water until you went and took a sip. And then it would become apparent. But there's lots of things dissolved in it, lots of minerals. Steel is a combination of a couple different metals. Most of your jewelry, rings, necklaces, earrings, etc., they're not usually ever, even if they say they're gold, they're like 14 karat gold or 24 karat gold. They're not pure gold. They're a mixture of gold and something else to make it more affordable. So, but you can't tell. You can't tell that it's a mixture. But you could, because those metals have different boiling points, you could separate them back out. It's possible because they haven't actually chemically combined. They've just physically combined. They haven't formed a new chemical. Those metals that are in there, the nickel and the gold, usually nickel is one of the things that they put in there, are still they're unique elements. They've just been combined in a mixture. The air we breathe is a mixture. It actually is only it's like 78% nitrogen, like 16, I believe, percent oxygen. So it's way more nitrogen than it is oxygen that comes flooding into your lungs with every breath that you breathe. But we can't see that because they're both odorless, tasteless, colorless gases. So we can't see it, so it appears the same. And then rain can actually carry a lot of stuff dissolved in it. We can't see it, so it's a homogeneous mixture. Okay, so now going back to the pure substances, we're going to kind of talk about the different types of pure substances. I like this graphic. Crystals are types of compounds. There are very unique things about crystals that kind of set them apart, but they are types of compounds. So for pure substances, we can have chemical elements and then just pretend this is compound all across it. We can have compounds. So examples of elements, they're going to be the purest substance. They can't be broken down any further and still be a substance. You're just going to break them down into protons, neutrons, electrons, things that make up an atom. So we can have tin, sulfur, diamonds are just pure carbon. Those are all going to be elemental. Then we can have compounds, things like sugar, water, baking soda, salt, different types of protein crystals, copper sulfate crystals. Okay, all of these are going to be compounds because they have a unique identity even though they're combinations of elements. So they're chemically combined, but you can't break them down any further and still have them be that thing. So I can't take carbon dioxide or salt. We'll use table salt. Table salt is NaCl, sodium chloride. Okay, if I break it down any further than 1 unit of sodium chloride, it's no longer sodium chloride. So I can break it down into sodium and chlorine, but then it's no longer salt. It's sodium and chlorine. So as a pure substance, it has to be NaCl. So let's first look at elements. Elements are a pure substance that can't be broken into simpler substances by ordinary chemical means. They consist of only one kind of atom. So examples, gold, iron, lead. So Fe is iron. I put some weird ones up there so that we can familiarize ourselves with some of the weird elements where their names are based on their Latin and not on their English word. So Fe is iron, not Ir. Iron, gold, Pb is lead, not Le. Atoms are particles in an element. Atoms are the smallest particle that you can break something down into and still have it demonstrate that compound's unique physical and chemical properties, or that substances, I don't want to say compound, that substances unique chemical and physical properties. So I can have 1 atom of gold and it's going to behave the same way as 5 billion atoms of gold. This is theoretical. This is a good example of theoretical science because no one has observed 1 atom of gold and seen how it reacts. But in theory, 1 atom of gold, it's too small to observe, should behave the same as 5 billion atoms of gold, which is much easier to observe. Still not very many, though. Wouldn't be very much gold. Probably about this amount of gold at the very end of a pencil or something like that. 5 billion atoms. Still not very many. It sounds like a lot, but when we're talking about atoms, they're so small. So I can have 1 atom of gold, 1 atom of iron, 1 atom of lead, and it's still going to have the unique chemical and physical properties of that substance. Atoms are made up of even smaller substances. Protons, neutrons, and electrons. These are called subatomic, because they're smaller than an atom, particles. And depending on how many of each there are, determines what kind of atom something is, whether it's gold, iron, or lead. So protons are positively charged, neutrons are neutral, they have no charge, and electrons are negatively charged. Now, an electron doesn't have an element identity. 1 electron, it's not like, oh, that's a gold electron over there. No, it's just an electron. How many electrons I have with how many protons and neutrons will tell me whether I have gold or not. But it's not like there is a gold proton and a gold neutron and a gold electron. It depends on the combination of them that gives me gold. Kind of like how I can have a Lego, and that Lego could build a model of the Death Star, but until I actually put that Lego in the model, it's just a Lego over here. It's a building block to something else. So they're just my protons, neutrons, and electrons, and they're building blocks to an atom of a specific substance. Ions, are charged atoms. So atoms can have a charge because I have positively and negatively charged material inside the atom. Depending on the ratio of those to one another, sometimes my atom can be charged. We're getting through a lot of vocab this week. Okay, lots and lots of vocab. A lot of these concepts we're going to be talking about further down the road in more detail, but we're kind of just hammering through them to get some vocab groundwork done. Now, not all elements take the form of just a singular atom. So like just on its own, one atom of it. Sometimes atoms like to bond together and form groups. They're still technically elemental. They're not considered compounds because they're the same element bonded to itself. So for instance, our noble gases, which are going to be things like neon and argon, krypton, these are going to only ever be found as a singular atom. And they're always found as gases, and they don't like to bond with anything, let alone themselves. Diatomic elements are going to be elements that bond in two atom units. So examples of those are going to be oxygen, or O2, which that 2 really should be like this, should be a subscript, O2. And the halogens, which that will make more sense down the road when I say halogens, what I'm referring to. There's a certain column on the periodic table where the halogens are found. These are going to be things like bromine, chlorine, and iodine. Those fall into the category of the halogens, and they like to bond with themselves. Cl2, Br2, they're not considered a compound because they're bonded to themselves. Compounds have to be different types of elements combined. So compounds are different types of elements bonded to each other. Elements can be found on their own, or they can be found bonded to themselves. Polyatomic elements are going to be elements composed of multi-atom units. So things like ozone or sulfur. The chemical formula for ozone is O3, and sulfur is S8. So notice there that oxygen has bonded to itself again. So there's 3 of them. Sulfur, there's 8 of them. 8 sulfurs all combined to each other, which is why there's a little 8 underneath it. Ozone is something that naturally occurs high up in the atmosphere. It makes our ozone layer, which actually helps protect us against the sun's ultraviolet rays. So very important. However, down here in the part of the atmosphere that we're breathing, ozone is actually very damaging to our lungs. And so there can be days, really hot days, where we can get ozone pollution, where ozone actually is created down at the level of the atmosphere that we're breathing. So they'll like announce on the news. They used to call them ozone action days. Now I think they call them, I don't know what they call them, green days or something. But there'll be days where they like tell people like, don't mow your grass and try to carpool and don't fill gas up at the gas station. Like they try to tell people that because combustion mixed with intense sunlight and heat actually produces that ozone, which can be very irritating, especially to people who have asthma. Okay, so that's elements. Now let's look at compounds. So notice the difference here in this substance. All the other substances on the previous slide all use the same color in order to help show you that it was the same element bonded to itself. Here we have a compound. Oxygen is in the green, hydrogen's in the blue. This is water, or H2O. It is a compound, and this would be considered one molecule of water. So compounds are made up of atoms from 2 or more different elements. So not just one element, like in the previous slide, but multiple different types of elements. And a molecule is the smallest independent unit in a compound. It's going to consist of 2 or more atoms that are chemically bonded together. So chemically, there was a chemical change that underwent that produced this. Now, this is considered a pure substance, even though it's not made up of only one type of substance. It's still considered a pure substance because if I was to separate them apart from one another, which I couldn't do in physical means, I'd have to do it chemically, which you can. You can take electricity and run it through water and get oxygen and hydrogen to separate off the water. So you can, it's possible, but then it's no longer water. It's oxygen and hydrogen. Water has its own unique set of chemical and physical properties unto itself, just like oxygen does and just like hydrogen does, and all three of them are different from each other. Which is why this is still considered a pure substance. That's a fundamental thing that we understand that pure substances doesn't just mean it's only one element. It just means I can't break it down anymore and still have it be that thing. Now in compounds, if I write a compound on the board, there's a few things that we need to take note of. So if I write H2O, or if I write H2O2, okay? These are two different compounds. What should give that away is that there's a 2 here and there's not a 2 here. So when we're writing out a chemical compound, we have to have the element written down. So what elements are involved? Hydrogen and oxygen are involved in these two compounds. And then we also use something called subscripts to show how many of each element is involved. So I have 2 hydrogens here, and then if it's 1, it's understood. Kind of like in algebra, where when you have x, it's understood that that's 1x. You don't have to write 1x or 1y. It's just understood that that's 1x. So if I don't have a subscript, it's understood that that's just 1 oxygen. Here, in this compound, this is hydrogen peroxide. Something else that we probably are familiar with. We still have 2 hydrogens, but now I have 2 instead of 1 oxygen. Both are clear liquids. One, however, is necessary for life. The other would kill you if you drank it. So, that 1 extra oxygen makes a huge difference. Makes a huge difference to the toxicity of this particular substance. So, compounds are going to tell the type and number of the atoms that are present, and we're going to use subscripts to tell how many of each element is present. There's another thing that can be used. This doesn't really get used, though, until we start talking about chemical equations and we start writing those out. But we also can use coefficients. Coefficients is a number that's going to go in front, and what that does is that number applies to the entire molecule. So this is saying that I have 2 hydrogen peroxide molecules, which means that total I would have 4 hydrogens and 4 oxygens because I have 2 whole molecules. Well, we're not going to actually use coefficients. It won't be until like November that we use those, but we will be using subscripts. Okay, so now we're going to diverge a little bit after we look at this last slide of review. So elements, one substance can be combined to itself, but it's only one substance. Compounds